Okay, determine whether each function represents growth or decay. You don't need to find the y-intercept. Y-intercept's easy to find. You just put 0 in for x. 5 times 3 to the 0 would be 5 times 1, because 3 to the 0 is 1, it would just be 5, but that's enough of that. Now we're getting to the point where we should be able to figure out if this is growth or decay just by looking at it. Okay, y equals 5 times 3 to the power of x. So this is like your a, this is like your b. I don't care if you label that, but the b is what you look at, the base on the exponent. Okay, this is bigger than 1. You're taking that initial amount of 5, multiplying it by something bigger than 1. That's growth. Okay. Now you're taking your initial amount, now you're multiplying it by something repeatedly that's less than 1, so that's going to be decay, that's less than 1. So that represents decay, 0.75. Okay, 3/4 is your initial amount, you're multiplying it by 3 over 2. Now is 3 over 2 less than 1 or bigger than 1? Well, since the numerator is bigger than the denominator, it's probably bigger than 1. Okay. Bigger than 1. That means growth. Okay, then we have y equals 0.2 times the base 1/5 to the x power. Again, 1/5 is less than 1 whole. Fraction with the numerator smaller, the top smaller, that's less than 1. So that is decay. Okay. Next page. Graph the function, identify the domain and range. So you got 2 times 5 to the power of x minus 2. Okay. Alright, so first off, if your independent variable is a power, it's going to be an exponential function. You want to parenthesize the base and the exponent, the whole thing. Now if the exponent's got an operation, you just separate that. Okay, so 5's bigger than 1, so that's going to represent a growth function. Okay, if that was a 1/5, it'd be a decay, but a growth, we're going to do an input-output table. And you're going to start with the positives, go to your negatives, and you have to have that asymptote line, or it's going to be wrong. Y equals, okay. Alright, so for growth we start with the positives, then we go into the negatives, and then some extreme value, -10, we'll find my asymptote. Okay, you can put -20 if you want. There's not a specific reason why I pick -10. I just pick a number, an input in that direction that's really, really out there. Okay, so 5 to the 2 power. 5 to the power of 2 is 25. So this is going to be 1 over 25. When you do a -2. 5 to the 1 power is 5. 5 to the power of -1 would be 1/5. Okay, that's how negative exponents work. They reciprocate the positive product. 5 to the 0 power is 1. Okay, now if you take 5 to the -10th power, pretty much 0. Heck, if you take 5 to the -20th power, that's such a small number, so close to 0. Okay. It approximates 0. Now, you got to adjust your table to fit the function. Okay, so within the exponent you got a -2. Within the exponent has the opposite effect to the x, so that would be +2. Then we need to multiply by 2, and then we need to add 4, because those are your outside operations. So +2 from that, then times 2 plus 4. So 2 plus 2 is 4, 1 plus 2 is 3, 0 plus 2 is 2, 1, 0, -8. Okay? Then you multiply by 2 and add 4. 25 times 2 is 50, plus 4 is 54. 5 times 2 is 10, plus 4 is 14. 1 times 2 is 2, plus 4 is 6. 1/5 times 2 is 2/5, plus 4 is 4 2/5. 1/25 times 2 is 2/25, plus 4 is 4, and 2/25. Okay. Then 0 times 2 is 0, plus 4 is 4. Okay. So the asymptote's 4. Now, unfortunately, we have to get to 54 on the y-axis, so we want to number that by tens. 10, 20, 30, 40, 50, 60. And then you need to set your asymptote where 4 would be, which should be somewhere in there. Pretty much halfway, not quite, but it's a sketch. Okay, so 454. So 1, 2, 3, 4, and then 54 right there. 314. 1, 2, 3, 14's right there. 2, 6, so 2 and 6 right there. So again, you're above the asymptote, and there's your graph. You're going up that way, and then here you're just getting closer to the asymptote. Okay, now the domain and the range. The domain, there's no restrictions for the independent variable. That's all. Okay, because you can go this way, you can go this way with it. The range, there is a restriction. That's why there's an asymptote. So we put y with 4. Okay. Remember, range is all possible values for the y. And if you look at your table, all your y values are greater than 4. And you can also tell by looking at your graph, they're greater than 4. Okay, next one. Graph the function, identify the domain and the range. So you're dealing with a logarithm. So the first thing you want to do is switch your x and your y. X occupies the y. It's the inverse function. Okay, now that's why there's a table off to the side here. So when I get the main table out of this, I'm going to have to go back and reverse it because I switched the x and the y. I wrote an inverse function. Now when we write an inverse, you got to get the y by itself. So log base 2 of y. Now you don't have any operations outside of the log base 2y. Okay, so you're ready to get rid of the logarithm. Remember how to do that. This is your base, x is the power, and y is the product. So your product you can write all by itself, which is the idea. Y is by itself. It's going to be base 2 to the x power. Not a very complicated function here. It's an exponent function. Okay, it's growth because 2 is bigger than 1. So I'm going to set starting with the positives. 2, 1, 0, -1, -2, because a -10 determines the asymptote. So I raised 2 to the second power, that's 4, and this would be 1/4. 2 to the 1 power is 2, and this would be 1/2. 2 to the 0 power is 1. 2 to the -10th power, it's the same as 1 divided by 2 to the 10th. That approximates 0. And again, you have to know the asymptote. Okay, now, I don't seem to have an operation with the exponent, so the x stays. And I don't have any operations outside the base and the power, so the y stays. So that is ready to go. But that's not what you get a graph. Since you switch the x and the y, you have to come over here and then flip your table. Invert your table. 4, 2, 2, 1. That's how you graph an inverse function. 1, 0. 1/2 -1. And then 1/4 -2. Now the asymptote's still going to be there, and it's still going to be 0. Okay? But instead of y being, and also you can do the 0, -10, you don't really have to. The asymptote's still 0, but it's not the y anymore, it's the x. So an asymptote with x is vertical. So on the x-axis, 0's in the middle. Okay? So I'd make a straight vertical line right there. Okay, so 4, 2, 1, 2, 3, 4, 1, 2, 2, 1, 1, 0, and then you know what's going to happen. You're going to hook that way, and then you go against the asymptote line that way. So now the domain range is flipped. Okay, it's going to be the range that's all, and then the domain is related to x, and I put the 0. Now look at your table. All these x values with the 0, they look bigger than 0 to me, so it's going to be greater than. Okay. Okay, write each equation in logarithm form. Write each equation in logarithm form. So, got a base, a power, then a product, okay? Base, power, product. You need to write it as a logarithm, okay? So, you write your log down. 2's the base, that comes to the other side. 5 goes to the other side, then the product 32 comes right after the base. It goes log base product equals the power. Okay. Next one, same thing. If you know how to do this one, you'll be fine with this one. Log base 5, negative 3 comes around here, that's your power, and then 1/125th. You can put the fraction in parentheses. I don't really care if you do, but technically a textbook would have you doing that. Okay, evaluate the logarithm. These are easy. Log base 2 of 8, what's that equal to? So you figure out how many 2's it takes to multiply to a product of 8. 2 to the what power is 8? 4, I think that's 8. So how many factors of 2 is that? It's 3. So this is equal to 3. Okay, log base 4 of 64. So figure out what that equals. So base 4 times 4 is 16 times 4 is 64. So how many factors of 4 is that? 3. So again, we have 3. Okay, log base 12 of 1,728. Okay. So the base 12 times 12 is 144. 12 times 12 times 12. Boom, right on the money. So again, I get 3. There's not a reason why it's 3. I just wrote problems, so it's always 3. 1, 2, 3. Okay, log base 3 of 1 over 81. Well, first off, you know it's equal to a negative. Okay, because instead of the integer 81, it's reciprocated to 1 over 81. So base 3, it's 9, 27, 81. Okay, but if it's 1 over 81, that's why our exponent has to be negative. It'd be negative 4. Okay, write the expression as a single logarithm. You have 5 log base 3 of x minus 3 log base 3 of y. So single logarithm. So you're writing log base 3, but you're only going to write it once. Then you make a parentheses. Put these darn coefficients to the back end of the product as exponents. That's the property we apply. Okay. And then you're going to have x to the 5th, and then minus means when we condense it, it becomes a division. So x to the 5th divided by y to the 3rd. That's your answer. Okay. Now you're expanding it out. Okay. So now you're going to write multiple log base 5s. Okay. So what factors? You got a 6, an x to the 2nd, and a y to the 4th. So I have 3 factors there. Then you put 6, x to the 2nd, but now the 2 comes around off the product, and that's now a coefficient on the logarithm. Okay, then y to the 4th. Okay, and the 4 comes around. So these are multiplication. When we expand them out, we write addition signs. Okay, and that's what we have. Okay, solve each equation. Now you're solving equations for variables. A variable in the problem's x. So what's special about the x here? First off, put in the operator. Okay. That x variable is a power. Okay, it's not in a logarithm. You don't see log or ln. Okay. The x isn't to any power. It's the power itself. So that variable right away we see is a power. So we want to parenthesize the base and the exponent, the 3 and the exponent, just like that, okay? Now, do you have any operations outside the 3 to the power? No, you don't, okay? So you're either going to go with COB or you're going to take ln if the base is e, but the base is 3, okay? That's your base right there. So since the base is an actual number, we use our COB. Change of base. So you circle that exponent, and you write that exponent, negative 2x plus 2, equal to the log over the log. Okay, so the base is 3, and then 81 is a product. That's 4. Okay, log 81 divided by log 3. Reason why I know, because I know 3 to the 4th power is 81, but the log over log will find, whoops, as long as your idiot teacher punches it in right. Yep, 4. So the expression negative 2x plus 2 is equal to 4. Now you solve using linear properties. You got times and plus, so you minus first. Takes you to 2. Then you divide by negative 2, and that's going to take me to negative 1 for my answer. Okay. All right, no, next one. 6 to the 2x power equals 10. So again, we're solving for x, and that variable is a power. Okay. Again, variable is a power, so you parenthesize the base and the exponent. Any operations taking place outside the 6 to the 2x power? I don't think so. Okay, so since the number's a base, you apply your COB formula, okay, by taking that power 2x and setting it equal to the log over log. So base 6 on bottom and the product 10 on top. This is going to be an irrational number because 6 to the what power is 10. It's somewhere between 1 and 2, but it's going to be irrational. 1.29. Then you apply linear properties and divide by 2. Linear properties means you just, x is on one side, non-x is on the other, and then divide. Okay, 0.645. If you want to go 0.65, I'd be down with that. Okay, number 17, 3 times log base 10 of x equals 15. Okay, so you're solving for x. Now, x is not a power. That variable x is in the logarithm. It's part of a logarithm. It's in a logarithm. Okay, so I'm going to put log above that. ln also means log. Make sure there's only one log or natural log. There is. Okay, that's not a problem. I don't need to condense. Parenthesize the log base and product and undo any outside operations. So log base 10, product of x. And you have an operation outside with the times 3, so you need to undo that. So divide by 3 before you worry about anything else. So log base 10 of x equals 5. Now you're either going to rewrite it into an exponent, or if you have ln, you take the e power from each side. Well, we don't have ln. We have a log with an actual base, so we need to rewrite it into an exponent. Okay? So this is my base, this is my power, and this is my product. It goes base, power, product. And you can tell, if you get lost on that step, just flip over to this right here, okay? And you'll be able to know how to take it from a log to an exponential form, okay? It says it right there, okay? So, we know we're going to have base 10 to the power of 5 equals x, okay? It says right there how to convert it to an exponent expression. Okay, 10 to the 5th power is 100,000. And I just got x, no exponents, nothing, so I guess it's just 100,000 as my x. Seems kind of weird, but that's right. Okay, number 18, 4 times e to the power of 2x equals 40. So we solve for x, and x again is a power. Okay, so you're back to solving a power. Parenthesize the base and the exponent. Base is e. Undo operations outside, so you need to divide by 4 before you do anything else. So that's 10. E to the power of 2x equals 10. Okay, then you're going to do your COB, but if the base is e, we can't do COB. We're going to take the natural log of each side, the ln. Okay, so ln, ln, that cancels, and then we have the linear expression 2x. Don't put 10, okay? You need to find the natural log of 10 on a calculator. 2.30. Okay. Divide by 2, and that's 1.15. So not that hard, you just got to switch your method. Okay. Okay, next problem. Solve the equation. You have ln, the natural log of x plus 2, plus ln, the natural log of x minus 2 equals 8. You have to solve for x. Okay. Now that variable is in a logarithm. Ln is a logarithm. If you want to put ln instead of log, you can, but ln is a logarithm. It's a natural log. Make sure there's only one log or ln. You got two of them, so you need to condense this into a product since it's plus. So you're going to take natural log, only one of them, and inside you put x plus 2 in a smaller parentheses, then plus means times, then x minus 2, and then you're still equal to 8. Okay, so you're good there. Now parenthesize the log, which is ln, the base, doesn't really have a base, and the product is this. Okay, if you want to parenthesize that. See if there's any operations outside. I'm not seeing any operations outside. Okay. Now we can't rewrite into an exponent because we actually have ln here, the natural log. So when we have the natural log instead of just a log with a number base, okay, we take the e power from each side. So you put little powers, and then you put e and e. So that cancels. But you need to figure out what this times this is. It's just the FOIL method. Not a hard one either. X times negative 2, 2 times x, and 2 times negative 2. So it's x to the second, negative 2x, positive 2x, and negative and a positive cancel. This is negative 4. Okay, so you have x to the second minus 4. Now you don't just put equals 8. E to the 8th equals a number, so you click second, ln 8. Okay. That's a big number, okay, but it's right. 2,980.96. Okay, so you're solving for x to the second power now, okay. Now it kind of changes. It no longer has a logarithm. The variable's to a power, okay. But we don't have to factor, because it's just x to the second power only, okay? So you use the linear properties. You know there's going to be two answers at this stage, because an x to the second implies that there's two answers, okay? But x to the second's all you have. You don't have x to the first, you don't have x to the third, so you're just going to x second only, okay? So that's when you use your linear properties to get the x to the second by itself. And then you apply the radical of a 2, okay? You use you use a root, okay? Essentially linear properties followed by a root, okay? So plus 4, so it's going to be 2,984.96. Okay, then you apply your root. It's always how to get an exponent off a variable. Apply a root of that degree to the other side. So it's an even root, hence the positive negative. There would be two answers. It's not a story problem, so I'm going to write both the answers. 2 second caret 2,984.96. 54.63. And that could be the positive or the negative. That one's kind of a hard one. Okay. Now story problems, these have gone pretty well. You have $500 in a savings account that will earn a 2% interest rate each year, compounded quarterly. Now I don't care what I don't do anything with the years, dollars over here. Okay, compound has its own equation. How much will the account be worth in 10 years? So the compound formula, compound within a certain number of years, P times 1 plus R divided by n, caret n times t equals a. Now we got to know what goes in for these variables. Remember, P's money and A's money, similar to how the A and the Y behave in the A times B to the X power. So P is 500, okay, and then I don't know where the A ends at, so that's going to stay A. That must be what I don't know. R is the percent, well I know that. Don't add it to 100 because that's why that 1's there. So 0.02. And quarterly means that's 4 times in a year, okay? Okay, then T is a number of years, that's 10, which makes sense that I know all these because I got to find the A. So P is 500, 1 plus, and then R is 0.02, N is 4, then N times T. So you're going to have 4 times 10 equals A. Now, when using this formula, you need to simplify the exponent. That's 40. And you need to figure out what the factor is, okay, by simplifying. So you take 1 plus 0.02 divided by 4, that's 1.005. Now you have 500 times the factor 1.005 to the power of 40 equals A. So I'm solving for A. Well, since the A variable is by itself, we simply evaluate the other side of the equation on a calculator, okay? You don't apply any of your inverse properties, okay? You just figure out what that equals out to, $610.40. Okay, number 19. Lumber company has 120,000 trees that need to be harvested. Each year the number of trees to harvest decreases by 7% because we're harvesting. How many years will it take the amount to be harvested to be cut down to 60,000? Okay, essentially half of it. Alright, so we got trees in years, not a compound problem. Okay, trees in years, it's per year. See, the compound formula means it's done multiple times within the same year. Okay, here it's just every year, so the X is years, trees is Y. So per trees per year. Again, the per year is a percentage, okay, and it's decreases, so minus. That's important for one single thing. So you know this is going to be an exponent function. I mean, you can make it, and you got to know your factor. This is going to be a decay because decrease, it'd be 100% minus 7%. That's 93%. So you move the decimal twice and it'd be 0.93 is a factor. Okay, now you can make a table 0, 1, 2. You put that as your initial amount. You multiply it by 0.93, but that's kind of a waste when we know that A times B to the X power gets the job done. So A, B, X, and Y. So A and Y stand for the same thing. They would be trees. So my trees began at 120,000 and they end at 60,000. Now the B I have, that's 0.93, and the X is the years, and that's what I'm trying to figure out. Okay, so you have 120,000 times 0.93 to the X power, and then the Y is 60,000. Okay, so we're solving for X. And again, what do I do when when the variable is a power? You parenthesize the base and the exponent. You undo the outside operation, which you have one here. You need to divide by 120,000. Dividing by the coefficient, and that's 0.5. 0.93 to the X power. And then since we have a number base, we want to go with the COB, the change of base formula. Okay, so the x equals log over log. So 0.93 is the, and then 0.5. So I take the log of 0.5 divided by the log of 0.93, and I get 9.55. So a little over 9.5 years. Okay, then my last problem. You buy a new mountain bike for $200. The bike decreases in value by a constant rate each year. After 3 years, the bike's worth $85. Calculate the percent change each year. So again, dollars in years. Years is X, dollars is Y. So per, dollars per year. There is no dollars per year, it's a percentage per year. We just don't know what the percent is. So it's an expo function, exponential function. The factor I need to just call B, okay? You couldn't do a table with that even if you wanted to, because you wouldn't know what the multiplier is every year. So A times B to the X power equals Y. Okay, so A, B, X, and Y. Okay, remember A and Y are the same unit. Y is dollars, so it'll be dollars and dollars. So 200 is your beginning, 85 is your ending. Okay. B we don't know, okay, so it's B. X is years, so that's going to be 3. Okay, so now you have your equation 200, the B remains B, but it is now to the third power, equals 85. And I have to solve for B, okay? Now B is not a power. The variable is not a power. It's to the third power. It's not in a logarithm. It's just to a power, okay? Well, we don't have to factor because B to the third is all we have, okay? So use your linear properties followed by the radical, the root, okay? Radical and root mean the same thing, okay? So linear properties followed by the root, and it would need to be a cubed root. So you divide by your 200, still got b to the third, 85 divided by 200, 0.425. Now find the cubed root on the other side, the cubed root, not a square root. It's a story problem, so we don't worry about plus negative anyway. It's an odd. It wouldn't even be a negative even if I was doing it. So 3 second caret, 0.425, okay, 0.75. So that's your B value. But you got to know how you got to the B value to find your percent. You need to take 0.75 and you subtract 1, and that takes you to negative 0.25. Then you move the decimal 2 forward to the right, and it's negative 25%. So that would be your factor. Or not your factor, 0.75 is a factor, but then the actual percent is negative 25%.